Welcome to this video about the development of a new underground surveying workflow. Group B is happy to share the results of a 6-week-long investigation into the possibilities of different technologies for the purpose of finding underground infrastructure. Since infrastructure plays an important role in the development, maintenance and expansion of a smart city, a way of accurately localizing underground infrastructure poses a big challenge for it. Thus, the goal of our project was to develop and test a workflow to determine the position of underground infrastructure by using different technologies than currently used. The currently used methods, namely the digging of test ditches, can be costly, intrusive, time-consuming, and does not always give a clear image of the complete test area. Therefore, the final method we were developing had the aim of being non-invasive, accurate, feasible, time efficient and lower on cost, since those are the areas in which the current methods are lacking. With the help of this workflow, a smart city and its inhabitants would benefit from the improved construction speed for underground infrastructure and would create an environment where a smart city can flourish. Our research method consists of four main phases. The first phase, we conducted literature research into existing methods and gathered valuable information from Dura-Vermeer, a company also interested in this development. Furthermore, we conducted research about possible technologies that might be used in localizing underground infrastructure. A second phase was a site visit with Erika de Vree from Dura-Vermeer, in which we gained beneficial information about how the current methods were performed and what impact that had on construction. The third phase was a test run, where we tested the technologies we had selected for our workflow and see how these worked. This phase was mainly conducted in order to get to know the technology and the test environment. Finally, the last phase was the development of workflow and a second test run, where we performed the workflow and assessed it, giving us valuable information for a final result. There are several methods to locate objects in the subsurface. Some are non-destructive, for instance, electromagnetic location, ground-penetrating radar, magnetometer survey, and vacuum excavation. Others are destructive, such as digging test ditches and such. Having said that, it was necessary to compare all the methods to know which performs better than others. Some criteria were defined to compare them on. These were accuracy, safety, time consumption, feasibility, and financial cost. Then a multi-criteria method was used to better evaluate and quantify the criteria, which might be conflicting. This was an analytical hierarchy process. After determination, we found that safety would be the most important criteria, and from that we ranked all other criteria. Once we knew the importance of each criteria, each method was evaluated according to the aforementioned criteria. For the criteria safety, accuracy, time consumption, feasibility, the measuring units were scorecards due to lack of detailed information and the complexity of measuring these criteria. And for final financial cost, the measuring unit was of course euros. After some calculations, it turned out that based on these criteria and our estimations, the EML and GPR are the best functioning technologies. Therefore, we chose these for our final workflow. Some description of these methods. The GPR is an easy-to-use machine to detect underground infrastructure by the use of radio waves. By walking over the area with the GPR sends out a signal and receives a response from the infrastructure. This gives a map of irregularities in the soil in the shape of beautiful parabolas. These parabolas indicate of some kind of underground object being present. Both its depth and its size can be determined from this. The EML is a much smaller, more maneuverable device, which uses electromagnetics to detect conductivity of underground objects, often electricity lines, metal pipes, or other conductive utilities. The EML works very well in addition to the GPR. This is because GPR is in difficulty finding smaller underground infrastructure at certain antennas, such as electricity or data cables. The EML can detect these objects. The way our method works is by using a line grid. This line grid can be physically or digitally put over an area to be investigated. This grid needs to be followed and clearly mapped so the location and direction of the different underground utilities can be determined from that grid. The notation of the position of the infrastructure can be done as shown on the slide. All data is written down: distance from the starting point, direction of the underground utility, and a depth estimation. This slide shows an example of the final results that our workflow can provide. The data collection was collected on the Elvingsweg at the location of the picture in the bottom left. The top right image shows what pipes and cables should be present based on the click cadastre data. The other two images show our GPR results in the bottom right and our visualization. Something to note is that the size from the GPR image we can hardly determine the size of the diameter of each pipeline, and therefore that is not representative. Multiple objects were found, however we have large difficulties identifying these objects. Of course our method isn't perfect. Therefore we have some recommendations for further research to improve our method. Firstly, testing with different frequency antennas could be a good idea. For field testing we chose an antenna which gave us certainty of enough depth but lesser resolution. For further research can be done in finding an optimal frequency which gives you the needed depth but also higher resolution. Secondly, further research can be done in finding a way to determine exactly what type of underground infrastructure the method finds. At this moment we can see that there is underground utility, we have an idea of how big it is due to the size of parabola, and we have a rough estimation of its depth. But for most of our findings we could not determine which type of infrastructure it was only using our method. Maybe the click data could be used to verify this. Lastly, the density of the line grid area could be further researched in to optimize the time spent to cover the large area. So, to conclude, we believe this workflow has the potential in regard to finding underground infrastructure and especially for verifying that there's nothing there. However, to improve the workflow's ability to find smaller objects and identify the infrastructure found, future research and development is needed. We'd like to thank you for watching this video and we're looking forward to answering any questions you might have.